In this video lecture, now we will go through packing efficiency, right? By packing efficiency, we mean the space that is occupied by particles in the crystal, right? And if you recall the previous video lecture, we have understood that there are some voids. When particles are arranged in 2 dimensions and 3 dimensions, there are some voids left, right? The voids are empty spaces that is not occupied by the particles which were represented by spheres, right? So those voids does not add to the packing efficiency, right? So let's quickly recall. This is what we have understood, that this is the way we can arrange the particles in 1 dimensions. We place the spheres which represent the particle side by side, right? And when you arrange the particles in 2 dimensions, there are 2 ways. Either you place the particles in the second row exactly below the particles in the first row, that will align the particles horizontally and vertically, right? But we have understood that that is not much efficient way of packing, right? Or the second way was, we will place the particles or the spheres in the second row in the depressions of the first row. These are the depressions, right? These are the depressions. So what we did, we placed the particles this way, right? Doesn't look good. This way, right? What we are doing is, we are placing the particles here in the depressions of the first row. Depressions between the particles in the first row, right? This is what we did. This is the third row, right? So this is the arrangement in 2 dimensions. Now, if you remember, when we built the structure of 3 dimensions, what we said, 3-dimensional packing is close packing is created when we place similar row on this row, right? That is, a row which is a 2-dimensional structure would be placed onto this row. And again, there are 2 ways to place the particles. In the other row, when you place the other row onto this row, there are 2 ways you can do that. There are 2 voids now, this one and this one, right? Either you place the particles, right, in the second row, in the second layer. These are layers. This is one layer. So to build a 3-dimensional structure, you take another layer and place it onto this layer, right? And the way is, either you place the either you place the spheres in the second layer onto these voids, or you place the spheres in the second layer onto these voids, right? So either you place it on this void or you place it on this void, right? If you remember, this is what we did, right? What we are doing is, we are placing the spheres in the second layer on these voids. This is what we are doing, right? And this created our HCP, hexagonal closed packing. Now, what I'm trying to show you is that these voids, right? These voids are empty spaces, right? Which will not add to packing efficiency. Whereas the space which is occupied by these spheres, right, will add to packing efficiency. So packing efficiency is the space occupied by these spheres, right, or the particles. So space occupied by spheres gives you packing efficiency, right? And your voids or holes, we also call these as holes, are your empty spaces, which will not add to the packing efficiency, right? Now we will calculate the packing efficiency in simple cubic unit cell, in body centered and in face centered, right? Now let's look at the first one, which is your simple cubic or primitive unit cell. Right, this is how we used to build it, right? In simple cubic, if you recall, in simple cubic, the particles are only present at the corners, right? Particles are present at these corners. These particles represent, these circles represent particles. These are particles, right? And we said that this unit cell, right, is touching other unit cells as well, right? And at the corner, since this corner is 3 dimensions, so at the corner, this corner or the particle at this corner is shared by 8 other unit cells, right? If you want to just see how it's shared with 8 other unit cells, you can just check the lecture on how to calculate the number of particles in unit cells, right? Because if you remember here, these are 4 faces, right? Below also there is a layer of unit cells, and there are 4 corners at the back of this, right? In 3 dimensions. If you look at in 3-dimensional structure, there are 4 corners at the back of it. So there are 8 unit cells that are touching this particular corner. That means the particle at this unit cell is shared by 8 unit cells, right? So in actual, this particle, since there are 8 unit cells, so 1 unit cell gets 1/8 of this particle, right? So 1/8 of particle at the corner belongs to unit cell, belongs to 1 unit cell, right? And if you look at this unit cell, there are 8 corners, right? And at one corner, only this much of the particle belongs to this unit cell, right? So number of particles is equals to 8 corners. 1/8 belongs to this unit cell at each of the corners, so you have 1 particle, right? You have 1 particle in this unit cell, right? Which is, we have already said, is spherical, right? We are considering the particles as spheres. Now, packing efficiency. Packing efficiency is, since now we know that in this simple cubic, simple or primitive unit cell, right, we have 1 particle, right, which is your sphere. So we need to calculate how much this sphere, right, occupies the unit cell, right? How much this 1 particle, since there is only 1 particle in this unit cell, right? So since we are trying to find this packing efficiency, and we said packing efficiency is space occupied by the spheres, right? So here there is only 1 particle, 1 sphere. So how much space this 1 sphere occupies in this unit cell gives you packing efficiency of your simple or primitive unit cell, right? So if we want to find how much space it occupies, right, packing efficiency, which is equal to space occupied by 1 particle, is equal to space occupied by this particle would be given by the volume of this particle, right? And the total volume of this cube, right? Total space in this unit cell is equal to the volume of this cube, right? And the space occupied by this sphere would be given by the volume of this sphere, right? So packing efficiency would be space occupied or the volume occupied by this sphere, right? Volume occupied by this sphere, which would be the volume of the sphere, volume of sphere divided by total volume. Total volume is your volume of cube, right? Because what we are actually doing is we are trying to find how much volume of this cube, right, is occupied by this sphere. That will give us packing efficiency, right? Now if you look at this sphere, this is the edge, this is the edge length of the sphere, side, right, side of the sphere, side, the length of the side of this, cube, the length of the side of this cube is A, right? And we know from mensuration that volume of cube is your side cube, right? Side is A. So volume, we are finding this, volume of cube is, we know the formula is side cube and side is A. So volume of cube is A cube, right? Similarly, now we have to find the volume of sphere, and if you remember from mensuration we know that volume of sphere is 4 by 3 pi r cube, right? R is the radius. Now how to find the radius? Volume of sphere. Volume of sphere is your 4 by 3 pi r cube. 4 by 3 pi r cube, right? Now let's see what is this r. If you just look at this face, look at this face, one face of this cube, it is these spheres, this is open structure, right? Open structure in which particles are represented by these small dots, right, at the corner of the cube, right? But in actual space filling diagram that we have studied earlier, these are spheres, right? And these spheres are touching one another, right? So it will look like this. This is how it will look like, right? Now this is the center of the sphere, right? And r is its radius. Similarly, this is the radius. This is the radius. R is the radius of the sphere, right? Now, and if you look at this, these two spheres are these particles, right? And these two spheres are these particles. And we know that the side of the cube, right, is A, which is the distance between these spheres, distance between the center of these spheres. So this R, right, the distance between the center of these spheres is A. If you look at this figure, right, if you look at this figure, these two are spheres, these spheres which are actually touching one another in this way, right? So this A is equals to the distance between the center of these spheres. A is distance between the centers of the sphere, which is 2r. So A is equals to 2r, right? So from here we know that radius is equals to A by 2, right? So r now we know is A by 2, right? So from here now we know the side A in terms of r, radius of the sphere. So in place of A is equals to 2r. A is equals to 2r cube, which is equal to 8r cube, right? This is your 8r cube. Now we will put the value of volume of cube and volume of sphere from here in this formula. This will give us your packing efficiency. Packing efficiency is equals to volume of sphere, which is 4 by 3 pi r cube, divided by volume of cube, which is 8 r cube. This and this will get cancelled. 4 by 3 into 8 pi, which is pi by 6. Right? Pi by 6 is your packing efficiency. And if you want to find the value of this pi by 6, this is equals to 0.524. Right? The value is 0.524. If you want to find this in percentage of packing efficiency, it's equal to 0.52, I'm sorry, this is 524 into 100, which is your 52.4. This much space, 52.4 space, is occupied by this one particle which is spherical in this unit cell, right? So I hope this is clear. It's very simple basic mathematics, right, where you're just using the formulas. And just remember one thing: when we are calculating packing efficiency, what we are doing is we are just calculating the space that is occupied by the particle, right, or the particles in that unit cell, right? And the total space in the unit cell, which is cubic, will get by the volume of this cube, which is your side cube. And using this 2r is equals to a, we calculated the side of this cube, right? Side of this cube, which is a is equals to 2r. So we have put the value of a, 8r cube, right? And putting the value of your volume of sphere, volume of cube here, we got pi by 6, which is 0.524. So percentage occupied by this sphere is 52.4%. This is the packing efficiency in case of simple or primitive unit cell, right? Now let's look at the second case, which is your face centered cubic, right, FCC. And we know that in FCC, this is how the diagram will look like. I'm sorry, let's just draw it again. In face centered, we have one particle at the center of every face, right? And we know we have 6 faces, right? So particles are present at the corners, right? And now from this we know that these particles are actually touching one another, and we have a particle at the center, right? Now if we join these, this will become a right angle triangle. Now again, this is the side of the cube, right? Here number of particles were 1, so we have calculated the volume for one sphere. Here we have to first calculate the number of particles. Once we know the number of particles, we will calculate the volume of sphere, right, divided by the number of particles, because all are spherical. Let's find out the number of particles. We know that in FCC, in addition to the particles at the 8 corners of the cube, we have one particle at the center of every face, and we have total 6 faces, right? And the particle at one's face, right, at the center of one's face, is shared by 2 unit cells, right? So to each unit cell, only half of the particle belongs, right? So number of particles, let's just quickly calculate. We have done the number of particles already in a different detailed video lecture. Number of particles would be half, right? We have total 6 faces in the cube, right? So total 6 faces, and at each face we have one particle, right? And that one particle is shared by 2 unit cells. So half particle belongs to each face into half, right, plus 8 particles at the corner, and from this here we know that at each corner we have 8 unit cells, so only 1 upon 8th belong to 1 unit cell, right? So plus 8 into 1 upon 8, this would be 3 plus 1 equal to 4. So we have 4 particles in FCC, right? So volume would be volume occupied by particles would be equal to 4 into volume of sphere, 4 into volume of sphere, which would be 4 by 3 pi r cube, which is 16 upon 3 pi r cube. This is the volume occupied by the sphere, right? Volume occupied by all the spheres in FCC. This is volume occupied, not occupied exactly, not occupied, it's volume of 4 spheres in FCC, right? Now we have to find the volume of cube, right? Volume of cube is side cube, so we will, using geometry or mathematics, we will find the length of this side of this cube, we will find the side of this cube, right? So this will look like, right, this is the particle at the center, right, and we have these 4 particles at the corner. These are not touching one another, but they are touching this center of central particle. All the 4 particles are touching the central particle, so the coordination number of this would be 4, right? So now what we have to do is, suppose this is your A, this is your B, right, and this is your C, right? And if we draw it here, these are the centers, we will join the centers. Here what we are trying to do is, we are trying to find the value of A side, right, in terms of radius of these spheres. This would be R and R, right? So this is your A, C, B, right? Now this is a right angled triangle, right? We know that now AC square is equals to AB square plus BC square, right? Now AC would be, this BC is, if you find it from, if you look at here, this BC is this, right, which is again equal to A. This is A, right? And this AB is again the side, the length, the side of this cube, which is again A, right? All sides of the cube are equal, right? So this is this BC, which is side, and this is AB, which is again this side, right? Let me just draw it over here neatly. Right, so this is your A, B and C, and there is a particle here. What you do is you join this, right? So this is your A, this is your A, this is your A, this is your A, right? So what we have done is, this is the particle, this center one represents this, and all these at the, and these particles, these 4 spheres represents particles at the 4 corners. right? So what we have to do is we have to find this A, right? So here, applying Pythagoras theorem, this AC square is equals to AB square BC square, right? And AB square plus BC square, which is your AB square is this length, which is A square, right? AB is A, right? So AB square is A square, BC again is A square. So this is your under root 2A square, which is again A under root 2, right? And your AC is, if you look at this, radius of the sphere is R plus R plus R plus R. This is your 4R, right? So AC is 4R is equals to A under root 2. Therefore, A is equals to 4R upon root 2. This is the value of side of the cube in FCC. Right, in FCC, this is how it looks like. So now we can calculate the volume of sphere in FCC, right? We have 4 spheres, right? Now it would be 4 into this we have already calculated. Now volume of cube would be your A cube, and A is your 4R cube upon root 2 cube, 4R upon root 2 cube, right? Which will come out to be 32, right? This would be 32 upon root 2 R cube, right? If you calculate this, you will get this. Now let's quickly, right, fraction occupied or packing fraction. From this formula we can find the packaging efficiency. Volume of sphere is your this volume occupied by 4 particles would be 4 into volume of one sphere. So here packing efficiency would be equal to volume of 4 spheres, right? 16 upon 3 pi r cube divided by volume of the cube. Volume of the cube is 32 r cube upon root 2. R cube will get cancelled out, right? And this will come out to be pi root 2 upon 6. If you calculate all these, you will get this pi root 2 upon 6, right? Now pi root 2 upon 6 would be, the value of this would be 0.74, right? So percentage efficiency would be equal to 74%, right? So packing efficiency of FCC is 74% and that of simple cubic is 52.4%. That means more space would be occupied by particles in FCC, right? So efficient packing would be in FCC, right? So this has more efficient packing. And one thing is packing efficiency of HCP, hexagonal closed. We have in the previous lecture we have understood what is hexagonal closed packing and cubic closed packing, right? And we know that cubic closed packing, CCP, cubic closed packing is same as FCC, right? And cubic closed packing is same as FCC, and HCP and CCP, right, has same efficiency, has same packaging efficiency, right? So packaging efficiency is 74% for all these three. CCP and HCP are equally efficient. The packaging efficiency of CCP is same as FCC, right? And HCP and CCP packaging efficiency is same as HCP. So all these three are 74%, right? I hope this is clear to you. Now in the next video lecture we will see the packaging efficiency of body centered, right? We have covered simple and face centered. The next video lecture we will cover body centered, right? So I hope this is clear to you. Thanks.